In this set of videos, we will discuss medical imaging systems. Primarily, we want to discuss the CT scan and the magnetic resonance imaging, the MRI, but we will mention other medical imaging systems as well. As a reference for this, I've taken some of the slides from the book Medical Imaging Signals and Systems by Prince and Links, published by Pearson, as well as some Wikipedia sites. There's an additional reference page available when we talk about MRI. So in medical imaging, the goal is to see what's happening inside the body. What you see in the body depends on how you look. I had a medical doctor friend who once told me that when reviewing medical images, you basically find what you're looking for, or tend to find what you're looking for. So medical imaging we tend to think of as giving us an exact image of what's in the body, but in fact it's highly open to interpretation. And so the presence of a good radiologist, and a radiologist who understands that just because you think you see something in an image doesn't necessarily mean it's there, is very important. And that's also why it's important at times, particularly when the diagnosis is serious. At times it's important to use multiple modalities of medical imaging because each one has its own advantages and disadvantages. And when talking about medical imaging, there are invasive measures and non-invasive measures. In this particular set of lectures, we will not discuss invasive measures, but there are a number of these that are used and they're fairly commonly used. One of these would be endoscopy systems. In endoscopy, you're basically passing a lighted fiber optic cable into the body, and this typically has a tiny camera on the end of the tube. It's passed into regions of the body, and the light illuminates the body region, and then the camera takes pictures of internal areas in the body. Two classic examples of this are bronchoscopy, which is used to look at the lungs, and colonoscopy, which is used to look at the large and portions of the small intestine. These give a picture of interior spaces. They're invasive and they usually require either a general anesthesia or a pretty significant sedation. They carry risks, obviously, of infection, puncture, but they do allow for minor surgical procedures to be done in tandem. So sometimes, along with the instrument, there are little tiny surgical tools that are included. So a classical example of this is balloon angioplasty, where balloons or inflating instruments are included that are used to reopen larger vessels in the heart, polyp removal during colonoscopy, and then there are some others. There are even endoscopy systems that contain small ultrasound systems embedded into the probes that allow for ultrasound to be delivered in very close proximity to the organ that's being measured or imaged. So non-invasive medical imaging basically is done by passing some sort of radiation through the body and then observing how that radiation interacts with or reflects from the body. Typical non-invasive medical imaging techniques include X-rays, CT scans, MRIs, and ultrasound. They can also be done by collecting radiation that's emitted from the body, and this is the classic PET scan, positron emission tomography. PET requires that some active material, radioactive material, be produced, that be injected into the body. So you have to inject radioactive material that has a limited lifetime. It will be taken up in different percents by different body parts, and then as the radiation is emitted, you're actually looking at images of body parts that have taken up that radiation. Different injectable materials can be taken up preferentially by different body parts. Some materials are taken up more by cancer cells than normal cells, and so this allows a contrast type of imaging to be done. So different techniques will show different things, and so often more than one technique can be used to provide complementary information when making a diagnosis. The figure here shows a basic just pictures of different kinds of images. This first one, A, is basically just an X-ray transmission. B gives you an indication of gamma ray emission from the body, so this would be like a PET type scan. Um, C is an ultrasound. Ultrasound has become much more detail oriented than it used to be. The resolution on ultrasound has improved significantly. And then D is a nuclear magnetic resonance, or MRI, of the spine. So you can see each one illustrates different things, um, and they illustrate it in a different way. So nothing really provides a complete picture. So let's talk first about the simplest imaging system that we've probably all had some experience with, and that's the simple medical x-ray. Basically, a medical x-ray works by transmitting radiation through the body. And different types of tissue will absorb x-rays at different levels. So what you see is you see sort of the remaining transmitted signal. Um, so X-ray comes through the patient. It's going to produce a two-dimensional image. Now the important thing to remember about an X-ray is that the image that you see on either the film or the digital detector is basically an integration of the body path through which the X-ray passes. So you don't get any resolution along the axis that's parallel to the ground or perpendicular to the X-ray path. You basically get an integration of what happened to the X-ray beam from the top of the, in this case, from the top of the chest to the patient's back. Now, sometimes that's okay because sometimes you're looking for things like broken bones. You're typically not going to use X-rays to provide highly detailed information. And the advantage of X-rays is that they're very inexpensive, they're very quick, and they're portable. So you now see at athletic facilities that you'll have an X-ray machine in the training room. Sometimes they'll actually have an X-ray machine on the field. In the military, you can have an X-ray machine present in the battlefield that's fairly easily portable. The main disadvantage of X-rays is that the X-ray radiation can cause cell mutation and hence cancer. Another disadvantage, it's not really a disadvantage, but it's a limitation. And the limitation is that you don't get any resolution in the plane that's perpendicular to the X-ray path, and the resolution overall is not great. But as a general rule, it's a first order kind of imaging. It can detect things like breaks in your bone. It can detect fluid in the lungs. It can detect foreign bodies, like if you have bullet fragments or other shrapnel in the body. That can typically be detected by an X-ray, especially if it's metal. So usually, by way of diagnostics, X-rays are one of the first diagnostic tools that are employed. Now, what would be nice is if we could see actually not only an integration of the radiation that's transmitted and how it interacts with the body, but if we could somehow resolve that into at this particular location in the head, in this particular plane, or in this particular plane, or in this particular plane, known respectively as axial, coronal, and sagittal, if we could somehow view a slice of what's happening at a very localized plane within that volume. And so this is basically done by creating tomographic images. So tomographic images require more sophisticated instrumentation as well as more sophisticated data processing. So computer-aided tomography is probably the most common type of tomographic imaging. It's usually one of the approaches that's done first because while at one time it was considered quite expensive, CT machines have become fairly common, and so doing a CT is no longer the expensive endeavor that it was at one time. Basically, the CT machine is going to provide a series of images that come from these slices from a chosen plane. They work by using an X-ray generator, and the X-ray generator itself is rotated around the object. And then X-ray detectors are positioned on the opposite side from the X-ray source. So this allows for images to be taken from several angles. So a visual representation of the raw data is called a sinogram, but that's not really sufficient for interpretation. So once you have acquired the scan, there's a considerable amount of image processing that has to be done to do a tomographic reconstruction. What that then produces is that produces a series of cross-sectional images. The pixels in an image obtained by a CT are displayed in terms of their relative radial density. So the pixel itself is displayed according to the mean attenuation of tissue that it corresponds to. And there are some scales for this that are standard. So the pixel is a two-dimensional unit that's based on the matrix size and the field of view. And that partially has to do with the resolution of your detectors. When the CT slice thickness is factored in, then the unit's known as a voxel. That's basically a three-dimensional unit. Um, One part of the detector can't differentiate between different tissues is called a partial volume effect. In other words, that means that if you have a big amount of not so dense tissues compared to a small amount of very dense tissues, then that can cause the same attenuation in a given voxel. So that's why people would like for their voxel size to be as small as possible, because within a voxel, you're just going to get information for that voxel, and you don't know if there is further structure within the voxel volume that might provide more information. So here's a picture of a CT machine. You can see it's round. The machine is going to rotate. And here's a picture of the CT scanner with the cover removed. Um, T here is the X-ray tube. And in the detectors, this sort of semicircular line would be your detectors. The um, the X-ray beam would be these red lines, and it's not just three, they're just showing sort of the outer limits in the center. Basically, the X-ray beam is continuous along here. And then the whole system rotates in the clockwise direction. The more you rotate the system, the more angles you get. The more angles you get, the better resolution you can have. So clearly the main disadvantage of a CT is because you are taking multiple images. You tend to have considerably higher radiation exposure in a CT than you would in a standard X-ray. So the trade-off is for what you get in improved resolution, you give up in additional radiation exposure. So a radiation dose, if you're talking about the irradiated part of the body, that's referred to as the gray unit. It's proportional to the amount of energy that the irradiated body part's expected to absorb. And so that gives you the physical effect on the cell's chemical bonds by X-ray radiation that's proportional to that energy. A sievert unit is an effective dose. So basically, um, in a year, you're exposed to radiation, background radiation on the Earth. And typically, in millisieverts, your whole body receives 2.4 millisieverts per year. So to give an idea of how much radiation dose is absorbed by the body compared to background, the effective dose is reported in sieverts. So for example, if you have a chest x-ray, that's 0.02 um, millisieverts compared to 2.4 in a typical effective dose of background radiation. So as you can see, it's a small percentage. If we come down and we look at an abdominal CT, you can see that a single abdominal CT scan is more than 3 times the typical annual background radiation received by a person. A chest x-ray is more than twice that amount. A colonography, depending on how it's done, is 6 to 11 times, or 6 to 11 millisieverts. So 2 to 4 times the amount of annual background radiation. And so you can see that there are some significant radiation, effective radiation doses with very commonly used CT scans. Head CT 1 to 2, so that's not too bad compared to some of the others. So basically, the result of a CT scan is a volume of voxels. And how we actually view that depends on what you're looking for and where you're looking and what the radiologist wants to see. But it can be presented in a variety of methods. And all of this is done in a post processing way. So, a thin slice is generally regarded as planes that represent a thickness of less than 3 millimeters. A projection is basically can be looked at as a maximum intensity projection or an average intensity projection. You can see the comparison here. So the maximum intensity projection clearly has a lot more fine detail. The average intensity projection looks a little more blurry. Um, the thin slice, you can see you're just looking at a very small area. A volume rendering in a virtual reality type environment can give you a three-dimensional looking picture, um, and you can do that at various different uses of data or thresholding. So typically all the volume renderings technically the volume renderings are projections because when they're viewed on a two-dimensional display, Um, so there's a little bit, it's a volume rendering is not that much different from a projection if you're looking at a normal 2D display, but typically in volume renderings you tend to have color and other things that give you some three-dimension like appearance of the data. So you can see sometimes some people claim that they can see more information from black and white. If you look at this maximum intensity projection, compare that to the high threshold volume rendering, it kind of depends on you as a person and on what you're specifically looking for. One thing to note is that when you do things like adding coloring and other things that change the nature of your image, you can sometimes be adding things that can be deceptive. So some people do prefer the black and white rendering because the color tends to sometimes draw the eye to places that you're not necessarily looking at. So the next lecture in the series, I'm going to break the lectures here. The next lecture on this material will be on magnetic resonance.